Okay, this is the problem we just finished with, and I had to terminate it kind of quickly because I was at the 15 seconds, and I think I've told you before, I make these videos and I upload them to YouTube, and then I bring them back to Folio. I can only do 15 minutes into YouTube. But after this, it is just arithmetic, and you do the arithmetic, and you've got the answer. Now, comment here, because I haven't done much of the arithmetic, and I'm not going to do the arithmetic because arithmetic's boring. If arithmetic really excited me, I'd be teaching elementary school. Your answers here need to come out to be positive. So the one I did do all the way out, it came out to be positive. These definite integrals are definite integrals that represent area. And if it is an area problem in our dimension, the dimension in which we live in, the universe in which we live in, area is positive. So when you do your calculations, if you come up with a negative answer, you've done something wrong. And if on a problem, on a test, if I've asked you to find the area all the way out and you come up with a negative answer, you best write me a note telling me that you know you're wrong. And it's always a good idea. If you know you're wrong, write me a note and say, I know I'm wrong, but I can't find my mistake. But especially on an area problem, if it comes out to be negative, you have to know you're wrong. And if you don't tell me you know you're wrong, you're actually going to lose more points that for some reason you think area can be a positive answer, or that area could be a negative answer. So these have to come out to be positive, and this certainly is going to come out to be positive. 4 to the 4th is 256, I believe. So that's 256 minus 16, that's way positive. So these have to come out to be positive because they're definite integrals that represent area. Now that I've said area problems have to have positive answers, I will then have some students that tell me that all definite integrals must be positive. That's not true. It's definite integrals that represent area must be positive. Definite integrals in general, anything can happen with those. And later on, when you get to Calculus 2 and you learn about improper integrals, some definite integrals can go off to infinity. So definite integrals can do anything, but definite integrals that represent area must have positive answers. Okay, let's continue. Let's do another one. Find the area bound by y equal cosine x, y equals sine 2x, and x equals 0. Now, the important thing here is you got to be sure, I've given you the picture, but you've got to be sure you find the right regions. That when I look at this, I see 3 regions. I see that little triangular region, this bigger triangular region, and that little kind of wedgy triangular sort of region. That there are 3 regions, and you got to be sure that what you use only, what you pick for the regions only involve the things that you know. So y equal cosine x. We'll trace that in blue. And if you're not good at labeling, identifying the graphs, take out your calculator and graph cosine x to see which one it is. But cosine, the basic cosine function, starts out at 0, 1. So y equal cosine x is this curve right here. So that must mean that y equals sine 2x is the other curve, so it's in red. And so it's this one. And then x equals 0, which is the y-axis. That's in yellow. So right here. So there I've just highlighted the things that are involved, the functions that are involved. So the region I'm looking at, find the area bound by only by y equal cosine x, y equals sine 2x, and x equals 0. The region bound by only the things I colored in. And so the region of the regions that are bound by the highlighted curves and lines is this little kind of bow tie region. Sort of looks like a bow tie. It is not this triangular region because this triangular region includes the x-axis, and it didn't say anything about the x-axis. It said cosine x, sine 2x, x equals 0, and x equals 0 is the y-axis. So it's only this little region there that I'm looking at. So now I need to know some points of intersection and x-intercepts. So that's A, let's call that B, and call that C. Now I am okay with that A is x equals 0. All of us should know that from, this is not quite the basic sine graph. It's the period has been adjusted, but all of us really should know that sine, kind of the basic sine graph, even when I move the period around a little bit, I have not adjusted this left or right. It starts at the origin. And then also we were told that this is x equals 0 there. So you do not need to compute that. That's okay to get from the graph. But B and C, and again, purposely suppressed the tick marks, B and C you got to calculate. And so B and C are the points of intersection of y equals sine 2x and y equal cosine x. And I've got to find those guys. Again, not good enough to estimate from a graph. Now, if I give you a picture and I draw a great big dot there and then I label that dot, you can believe my labeling. But if it's just kind of, well, it looks like it probably crosses that, no, not good enough. But if I label something for you, you can use it. But I didn't label anything here. To find points of intersection, set the functions equal to each other and solve. And so in this case, sine 2x equals cosine x. And we got to solve that guy. Go out a little bit so we can see it more at once. Okay, recall. Sine 2 theta is 2 sine theta cosine theta. Yep, trigonometry rears its nasty little head. The reason why I want to do that is it's way easier to solve trig equations when every trig function has the same argument. Solving trig equations when you've got two different arguments, two different angles, 2x and x, way hard. So trig identity, sine 2 theta equals 2 sine theta cosine theta. So our problem becomes 2 sine x cosine x equals cosine x. One of the standard tricks for trig equations when I've got two trig functions in there, see if you can use some factoring. So I'm going to set it equal to 0, and then I can factor out that cosine x, leaving behind a 2 sine x minus 1 equals 0. And now it's factored and equal to 0. So I can split that up. And so that's cosine x equals 0, 2 sine x equals 0. And then this side over here is going to give me sine x equals 1/2. And I'm going to draw a rough mock-up of the graph again. So the graph, I'm going to draw my axes in light blue. I didn't bring a black pen. Rough mock-up of the graph. I got to see the graph momentarily. I'll put that back up there in a moment. We had the cosine x in blue. And we had the sine 2x in red. And where is my yellow pen? And then this was that. And then we said it was this little bow tie region. And this point here was A, B, and C. So there's my graph again. So now looking at this, and I want to know where is cosine x equals 0. Cosine x equals 0 at pi over 2. Now, it also equals 0 many other places. Now, why didn't I take many other places? Because this is the first place when I have the basic cosine graph here, that y equal cosine x was in blue. I've got the basic cosine graph here, the first place that it equals 0. So the first place it equals 0, pi over 2. This graph isn't going on forever, that I'm doing so I'm starting at the origin, start here, go to here. The first place that cosine equals 0 is pi over 2. Then I ask myself, where does sine x equal 1/2? For what angle in radians does sine equal 1/2? And sine equals 1/2 at pi over 6. Now, if I hadn't suppressed the tick marks, that should look reasonable. So when you have your own graph on a calculator, those should look reasonable. But you have to actually calculate it out. And so there's my picture. If you like seeing the little rectangles to help you visualize what top and bottom is, and it does help some people visualize top and bottom, notice we have two regions. Let's call this A1 and A2. And so my total area will be the area of A1 plus the area of A2. A1 starts at 0. That was x equals 0. B was x equal pi over 6. And C was x equal pi over 2. So A1 goes from 0 to pi over 6, top minus bottom. So on this region here, the top curve is cosine. The bottom curve is the sine 2x. Then the second curve, top minus bottom, it starts at pi over 6 and goes to pi over 2. And again, top minus bottom, but this time the top is sine 2x, the bottom is cosine x dx, and there are the integrals that are going to do it for us. Now we're going to go ahead and integrate this out, but if the problem were to say set up only, this is where you would stop for the set up only. And I would be expecting to see where you calculated the points of intersection and then the integrals. And again, if the graph is not provided, you need graphs on here because you've got to really be able to determine top minus bottom. There are algebraic ways to do that, but the pictures are so much easier. Now I'm going to end this video here and start again, and we will actually integrate this and we will work this one out quite a ways because it involves trigonometry. So let's start the video and then we'll finish it up on the next video.